Hey guys! Today, we're playing with EEG technology. The setup was hand-built by college students. And now we're trying to detect fatigue with it. And it can even read your movement intentions. Cool, right? Now, let's check out the hardware design. Now, the hardware design is reported by Janley. First, let's talk about RPMP selection. Since brainwave signals are tiny, only 10 UV to 100 IV, you'll need a precision OPMP like the 8620B. Regular op-amps like the LM358 just won't cut it. The 8620B has an ultra-low input offset voltage of around 50 UV with variations as small as plus or minus 25 UV. That level of precision is a must for this project. We're setting the gain to 100, which means the max output offset will be just 5 millivolts, perfect for our needs. Here's the basic circuit design. Since FASM doesn't have the 8620, we're simulating it with an LM358 equivalent. The signal goes through low pass, high pass, and bandstop filters, then gets amplified in 2 stages, 100x each for a total gain of 10,000. This boosts a 100 UV signal all the way up to 1 volt for the STM3 to F4 MCU to read. The filter cutoff frequencies are set using the classic 1 over 2 pi RC formula. Now, here's a weird issue we ran into. When 2 electrodes touched, they somehow generated a voltage difference between them, causing the first op-amp to saturate. Turns out, there was a DC offset of over 100 millivolts, way bigger than the actual brainwave signal. Like 1000x bigger? You'd think the high-pass filter capacitor would block all DC, right? Nope. After testing, we found that the conductive gel between the electrodes was creating about 40 millivolts of voltage. Fresh gel was better. Old gel made it worse. According to DeepSeek and Kimi AI, this happens because of a redox reaction basically. The uneven gel turns the electrodes into a tiny battery. Here's the difference between ideal and real-world components. In theory, filters work perfectly. But real capacitors have leakage resistance, which messes things up. We fixed it by swapping in ceramic capacitors, which behave much closer to ideal. Now, pay attention, let's dive into the MATLAB data. The graph on the right shows time, x-axis versus frequency, y-axis. The yellower the color, the stronger the signal. Blue means weak. We also use signal-to-noise ratio, SNR, to check electrode contact impedance and separate different brainwave bands. For example, if we feed a 7 Hz signal into all channels, the left graph shows the energy landing in the theta band, 4 to 8 Hz. Next up, hand movement imagination tests. After dozens of trials, accuracy was nearly 100%. Hand movement imagination, how it works. You sit still and imagine moving your left or right hand. The brain's C3 and C4 electrodes pick it up clearly. When imagining left hand movement, we see a spike in 8 to 12 Hz energy over the right brain hemisphere, and vice versa for the right hand. Bonus discovery, this setup can also detect EEG, heart signals, and even track eye movements. Turn my eyes to the left. Turn my eyes to the right. Turn my eyes upward. Turn my eyes downward. Blink. Open the mouth. Thanks for watching.